You can start now.
Yeah, good morning, everybody. Thanks for joining one more time. My name is Manish, and yesterday we had gone through the management system, well-integrated management system, along with some standards, international standards. I'll switch on my camera for some time so that you can see me for some time, and then we will start. So before I start, I just want to give you an introduction about the well-integrated technical section of which I'm a member of, and I'll just take you through the website. This is the website for well-integrated technical section, and these are the board members. There are other technical.
Sorry, the image is not clear. Like we see the presentation only.
You are not able to see the website?
No, just the presentation now.
If I change the screen, you're not able to see.
Yeah, you can change the share screen or stop it and
Share again.
yeah.
It's not here. No, I'm not able to share the screen.
Can you now?
No, I'm able to see this screen share, but here I cannot see the website which I wanted to show you. This is Safari. Okay, sorry, it's here. Yeah, I got it. So you can see how. So you can navigate from the SP homepage. You can see the SP homepage now, I hope.
Yeah, now it's clear.
Okay. Yeah, I think you have to choose the individual screen. That's why. So this is the SP homepage. There are several communities. You can access the community from here. Once you click the community, it'll take you to the community page. And here we are under completions community page. You can choose any of the technical sections, and well integrity is one of the technical section under completions. So if you choose technical section, it will list down all the technical sections on the left hand side, and you can join any of the technical section, be it well integrity, sustainable development, plug and abandonment. You have interest in hydrogen, data science, artificial lift. So there are several options to select. If you select well integrity, it will take you to this web page. To hide this one. Anyway, so it looks like it's not working for me here. Yeah, this is the well integrity technical section page, and you can join the community by clicking here. Also, it will take you to the SP profile page so that you are able to join it. In future, we will be opening board for the student chapter also. I'm here as learning and development officer in the well integrated technical section. In future, I will be opening positions for the student chapters also, to engage them early on in all of the technical sections, and we are starting with the well integrated technical section. Just wanted to give you a brief of this, and then I'll go back to my presentation. So this is the one. Okay, So I'm back on the presentation slide. So we covered first 2 points. Today we'll be covering diagnostics to identify well integrity failures, then some brief about the risk assessment and about the plug and abandonment. So there are several levels of competence for each of the courses, starting with awareness. Second level is knowledge, then skill level, and then mastery. So you can say what I am trying to present is basically in the knowledge or awareness level presentation, and not going into very much details, because each of the subject is quite in detail and might take some time to present and explain all of you. An interactive section would be much more appreciated, because then there are some doubts and which need to be clarified before we move forward. So when we talk about diagnostics, means we are seeing some failures where we can diagnose what kind of failure is happening. And the second stage after identifying the failure is to do a remedy, or you cure the failure or repair the failure, which will range from a simple wireline task to a detailed work code. And it could be a rigorous solutions or a rigorous intervention, which will also solve the problem or mitigate the risk. So again, the disclaimer is that because I've copied most of the pictures from internet, and if somebody objects, please do let me know. Or if you see anything which is a miss or spelling mistake, please also do let me know. So I'll play a video. This is an incident. Probably you would have seen this incident or heard about it. It was 2 years after the Macondo incident. This is
methane gas is continuing to flow from Total's North Sea Elgin platform after it sprang a leak on Sunday. The leak is believed to be.
Sorry, can you hear the audio?
Yeah.
Okay, let's start one more time.
Methane gas is continuing to flow from Total's North Sea Elgin platform after it sprang a leak on Sunday. The leak is believed to be coming from a non-productive reservoir situated above the main reservoir. There is growing concern that the leaking gas could cause an explosion if it comes into contact with a flare burning on the main platform, around 90 meters above the gas leak. Currently, the wind is blowing the gas away from the flare, but Total has said it expects the flare to burn out by itself. Should the wind change, there is a risk of explosion. Options for plugging the leak currently being explored include a dynamic kill, where fluids are pumped into the well to relieve pressure at the wellhead. Another option is a relief well, but this would take several months to complete. Sea and air exclusion zones have been enforced around the platform as a safety precaution.
So this is an incident which had happened in 2012, and it caused major setback for the company. The production had to be stopped almost for a year, and there was a major loss to the company, and including a penalty imposed by the government for polluting the environment, which is by release of methane gas. So this is the schematic diagram for this particular well. The shallow gas pocket which was shown contributed gas into the A annulus, which is between the tubing and the production casing. So this production casing corroded, leading to further corrosion in the next casing, which is intermediate casing, the surface casing, and the conductor finally, and it came to the atmosphere. So what went wrong? Because they had seen some pressure in the C annulus, which is between the intermediate casing and the surface casing. However, the well was planned to be plugged and abandoned. During the intervention, the pressure increased, and probably the failure would have been waiting to happen. So what has happened here is two things. There would have been poor cementation for this particular casing, which would have allowed corrosive fluids to interact with the casing to corrode and make a hole into it, whereby the gas entered from the shallow reservoir into the production annulus, the A annulus as it's called. And subsequently, over a period of time, this corroded, and subsequently further all the casings corroded and eventually led to the failure. So such cases, what happens is that it doesn't happen overnight. The failure doesn't happen overnight. It gives us sufficient time either to diagnose or to properly assess before the failure actually happen. Our intention is that failure should not happen in a well. So this is the summary of the incident. It happened on 25th March 2012. There were 219 persons in the adjacent platform which had to be evacuated. And at the time of incident, the field was producing around 120,000 barrels, which is quite substantial, amounting to 7% of UK's production, resulting in release of methane gas to the environment. The cause of the incident was identified as the corrosion in the casing, which I was trying to express. A relief well had to be drilled. So there was an additional cost for the relief well, and a semi-submersible rig had to perform a top kill operation by pumping heavy mud into the well to kill the particular well. And the bottom kill was performed by a relief well. So these are additional intervention costs to cure the problem, in addition to the stoppage of production. You see the dates. The leak happened in May 2012, and almost a year later, the production could be restarted. And it is told that only they could start 50% of the production and then gradually increase to the full production. So overlooking of well integrity issues has a major consequence for the company in terms of cost, reputation, discontinuity in production. The company cannot meet the production targets, etc., etc. This is another incident which happened in Los Angeles state area. This release resulted in a release of a huge quantity of gas into the environment. The carbon footprint was said to be larger than the impact of the Deep Horizon leak, which is in the Gulf of Mexico for the Macondo. What happened here was that it was an old field. The reservoir had depleted. So they were using the reservoir to store gas to be supplied for the local community people. It's a so-called company. So South California Gas Company, SoCal Gas, the company is that. So they were using the existing wells and the reservoir to store the gas. However, over the period of time, this was a very old field, and because of degradation of barriers, the casing had degraded. There were no safety valves, downhole safety valves there. So there were a lot of concerns in managing integrity for those wells, and which had resulted in a huge impact in the environment. People had to be evacuated. A lot of people years later also had breathing trouble and infection because of this release of gas. This is another well integrity concern incident happened. Another incident happened in 2002. It was a BP well, wherein explosion prompted BP to shut down 150 well. This is a news article. So what happened in this particular well was that the well was a gas lifted well. It had an annulus pressure. So when the well was started up, the hot fluid were brought to the surface. Alaska means it is a very cold area. So the temperatures outside were very less. When the hot fluid were brought to the surface, and the A annulus fluid got heated up, and the pressure in the A annulus increased substantially. The pressure increased to 7,700 psi during startup, which resulted in a surface casing burst. and release of that expanded gas, resulting in a small fire and injury to the wellhead operator. So this is a pictorial description of what had happened. This is a cold system on the left-hand side, and the right-hand side is when the hot fluids were brought to the surface in terms of the production. And in turn, the heat transfer happened to the annular fluid, and which caused it to expand. And the pressure for the gas, which is a small gas cap was there, the pressure increased. So the temperature increased from 45 degree Fahrenheit to 115 degree Fahrenheit. And the pressure from 2000 psi increased to 7700 psi, which was more than the burst rating of the surface casing, which was published burst rating for the casing which was used was 5380 psi. So this caused the surface casing to fail and the incident to occur. This also resulted in the stoppage of production and a lot of impact to the company. This is a news article which says that the production was around 60,000 barrel a day, which was around 6% of that area of North Slope production. So what were the contributing factor? So we talked about barriers yesterday, that it's not just the physical barrier, but there are other barriers, soft barriers also, which in terms of the competence and the training of the people, which makes an impact to the overall integrity of operations. So the pad operator who was there at the site starting up the well was advised that the well integrity had verbally issued a temporary waiver clearing this particular well to start without proper assessment of the situation before starting. So there was a discretionary power which was used by that engineer to convey the message to the operator, and no written communication was there. No high pressure hose was available on the pad for that particular well to bleed off the pressure before the startup. No specific engineering analysis or guidance address startup procedure or when the pressure should be bled. Though no clear procedure or written down guidelines for the wellhead operator to perform the task. There was lack of clarity and understanding related to problem for the well startup. And the operator training was also a questionable issue. So you see, an incident could happen, everything could be fine, all the barriers could be okay, but if the competence is not there, and it could also lead to a failure or integrity incident. So this sets us the background. So well integrity is a teamwork. It is not just one person. Well integrity is mostly a technical expert who is sitting in office, guiding and creating operating limits, advising people, writing down procedures. But it's a teamwork. All the stakeholders are involved, be it reservoir engineer, geologist, petroleum engineer, drilling engineers. At the site, we have the maintenance people who are production operators, pad operators. There's all stakeholders contribute to ensuring the integrity of the well is maintained. So having a clear goals and deadlines is very essential. Understanding the strength and weakness of the people and helping the less inexperienced people. Good line of communication between the team members, which is very, very essential. We have seen in the previous slide. The people should not be afraid to ask questions just to clarify doubts, what happens, what to do. So it is very essential that the communication, these all points highlight about the communication issues and other barriers between people which inhibit the right message to be transferred, which is very, very essential for maintaining clear integrity targets. So I have listed down some of the well integrity issues which could impact the well or elevate the well risk. It could be sustained annulus pressure. It could be in several different annuluses or one of the annulus, like production annulus or cemented annuli, or could be a combination of those pressures between the annuli. We could have a downhole safety valve failure. There could be failure in the mystery valves. Offshore conductor is very important because it acts as a structural member, and loss of strength could lead to failure in the well also. Often, two or more failures can complicate the diagnostics and also may lead to worsening of well-integrated condition and thereby raising the risk level. So again, this is a different picture showing different casing, a schematic for the well, starting with the tubing, which is in red, which is having a downhole safety valve. In most of the cases, it is surface controlled subsurface safety valve. We have packers here, which act as a primary barrier. Then comes the production casing, and below, from below the shoe or perforate through perforations, production is taken. On the subsequent annuli, there could be cement behind the pipe to the surface, or could be as per the design of particular well, based on the threads available in particular region. So what we have seen is that the first possible failure could happen because of a pressure in the A annulus. So A annulus pressure could be because of thermal, as we have seen in the BP case, wherein when we start up the well, whatever fluid is there, be it completion fluid or gas, might expand and cause show a pressure to the pressure gauge which is installed in this wellhead. But when we bleed this pressure, then this pressure should go off, and only the incremental heat which is brought will cause the fluid to expand, and the rate of increase of the pressure in this A annulus will be substantially less. The pressures in subsequent annulus could also be contributed by thermal, but the effect of thermal is very less in the subsequent annulus, which is B, C, D annuli, and which will also be cured if we bleed the pressure, so it will not come back. If a pressure is bleedable, the situation is okay. Many times we have seen that the pressure becomes unbleedable, means that you open the valve, the pressure is continuous, the pressure does not go down, or the pressure may go down. We start at 500, it might go to 100 psi, and then there is a stable flow. So this stage is called unbleedable pressure. The second is we bleed the pressure. Suppose there is a 500 psi, we bleed the pressure, it becomes 0 psi. However, within a certain period of time, say after 24 hours, it again builds back. So this is called a sustained pressure. This indicates that there is a communication from down, which is feeding the annuli. It could be any of the annuli because of failure of the barrier. It could be cement failure in the cemented annulus. It could be packer failure in the production annulus, or it could be there could be a leak in the tubing. There is a word which is written as MAVOP. It is called maximum allowable wellhead operating pressure. It is like an operating limit for each of the annuli, with an instruction that this pressure should not be breached the pressure in the annuli should not exceed this MAVOP pressure at any point of time. API, ISO have their own different recommendations, but as calculation, when we calculate for any envelope like A annulus envelope or B annulus envelope, we calculate MASP, which is maximum allowable surface pressure. So MASP is the least of the strength of all the elements within that envelope. So we calculate the strength of, suppose we are calculating MASP for A annulus, then the collapse for the tubing, burst for the production casing, tubing hanger cavity pressure test, the packer pressure test. So whatever is the lowest value becomes the MASP for this envelope, A annulus envelope. And 80% of MASP we consider as MAVOP. So there is a safety factor which is built into it for the MAVOP, and this becomes the operating limit for that particular annuli. This picture is again, which I had shown earlier yesterday. This is from ISO 16530. These shows various leak paths which might occur because of the failure in the barrier. Many of the failures might not show to the surface in terms of pressure because it could be an internal leak. However, there has to be some diagnostics to identify the failure happening. So if a failure in, suppose in the tubing happening, this point number 9 means there is a corrosion, and immediately the fluid in the tubing will be will move to the A annulus, causing pressure to rise here. Or if there is a breaking of the cement, the pressure, suppose there is a pressurized zone, it might cause pressure in the B annulus. So similarly, for each of the pressure, we have a different diagnostic to be performed to assess the situation. So well integrity engineer is like a doctor which is only looking at the symptoms which are there on the surface, because our barriers may be thousands or tens and thousands of feet below the surface of the earth, and we have to assess the failure in the barrier. We have some tools which can be lowered in the tubing to perform logging operations to assess the situation. However, still it is like diagnostics, like a doctor does the diagnostics for a patient. So again, coming back to the sustained casing pressure, which I was mentioning, a sustained casing pressure is an excessive pressure that comes back once it is bled down. It is defined as a pressure in any well analyzed that is measurable at the wellhead and rebuilds when we bleed it down. Usually we say if it is builds back in 24 hours, but if it is 30 hours also, it will be considered as a sustained casing pressure. And this pressure is not solely caused by temperature fluctuations or an operator imposed pressure, like it could be a gas lifted or any other pressure which is there applied in the annuli. So what are the guiding forces or guiding instructions for the well integrated engineer? That all accessible annuli should be monitored. A pressure gauge should be installed in all annuli to monitor this pressure. And this pressure has to be maintained within the operating limits, within the maximum and minimum operating limits, which is prescribed for each of the annuli. There is also an instruction, if the well is gas lifted well, then the pressure in the A annulus, which will be the gas injection pressure, and the B annulus pressure should be continuously monitored. Because if there is a failure in the production casing or a breach of the barrier, which will cause pressure from the A annulus be transferred to B annulus, then it has resulted in a failure, and it could be a more risky situation. Yes, I think somebody would like to ask a question, please. Can you mute, please?
Hello, Mr. I have one question, if you don't mind. Why this cement is not up to the surface?
Yeah, so cement by design is not required to be at the surface. So in most of the standards, it is mentioned that only it is mandatory, it's a shall requirement for the cement to be surface for the surface casing, because we have aquifers behind it. And for the subsequent casing, it has to be by design above the shoe of the previous casing, so all the barriers are there. However, in case of a subsea well, just to take care of the expansion of the fluid for the cemented annulus, it is intentionally left below the casing shoe. Imagine a situation of a subsea well where we do not have the wellhead at the surface. We do not have a provision to bleed this pressure in the B annulus if the pressure arises because of thermal. So by design, it is left below the previous casing shoe to allow any fluid to be expanding, to go to a permeable zone as like an auto bleed off, and not cause the casing to burst for this one and collapse for this one. This is by design. Actually, it's not for all the situations, like for in onshore or like for the wellhead towers where we have dry trees, the cement could be way above. but it is not mandatory for all the casings to bring cement to the surface. Is it okay? So most of the operators in the Middle East insist to bring cement to the surface. However, when we see the operations in the North Sea and in US, the cement is not brought to the surface. There are two reasons for it. For the subsea, as I mentioned, that it causes an auto bleed off system for the annuli in the cemented annulus. And the second is when we do the P&A, it is easy to cut and retrieve the casings at the time of P&A. But each well needs to be designed for triaxial loading and other calculations to determine the cement heights. But there is no such guidance to bring cement to the surface for all the casings as a mandatory. But it is good to have, but not essential. Could I answer, or there is some more questions on top of it?
No, thank you so much. I got it. Thank you.
Okay, most welcome. Most welcome. So these are some of the paths, examples of possible leak paths. These are more specific to the sustained casing pressure in the cemented annulus. So what are the causes and consequences? The causes are here. The sustained casing pressure is caused by gas migration from a high pressure subsurface formation through a leaking cement sheet in one of the cement annuli. It could be one or more of the cement annuli. It may also be caused by defect and leaking tubing connections, downhole accessories, or wellhead seals. So any of the barrier could be breached. And it could also be resulting in the degradation or failure of well barrier, like corrosion can happen, or normal erosion can happen for the tubing where the flow of fluid is taking place. The leak develops either due to poor cementing job, during production by temperature and pressure fluctuations, corrosion, erosion of tubing or casing, other type of well integrity failures. So that's why we always insist to do the job right at the first time. Like when we are drilling a well, we ensure that cement should be the surface, all pressure should be tested, the cement bond log should be perfect, there should not be many microannulus, cement should be fully supported behind the pipe, at least across aquifers or the fluid, or if there is a corrosive fluid behind the pipe. So that's why we always push drilling to make sure that whatever we plan slightly, keeping some safety factor and doing the job perfect at the beginning. You can imagine if we miss any of the points, then it will cause a threat to the later stage of well life. So what are the consequences? If there is a sustained casing pressure, it will manifest, it will show up itself at the wellhead, and it cannot be reduced, and it's irreducible casing pressure. It might result in loss of containment with environment and material damage, and or production or human loss. There are several instances happening for this one. Can occur throughout the lifetime of the well. So it might not happen. A poor cementation might not cause problem immediately, but over a period of time, it might get further degraded, might cause the corrosive fluid from the reservoir to enter or be in contact with the casing and cause corrosion and a failure of this barrier in subsequent period of time. So it's a well integrity challenge, and it has been a focus of most of the operators and regulators. There have been several regulations from US, Eurozone, Canada, how to manage sustained casing pressure. So there are monitoring and detection plans, mandatory monitoring and detection plans. Like in our country, we have monitoring of annulus pressure of at least once a month. And some of the wells which are gas lifted have to be continuously monitored through a real-time monitoring system. We have to evaluate those annulus pressures, determine what is the acceptance, what level of annulus pressure we can sustain in terms of the operating limit. And then if we see any pressure, there has to be mitigation measures to reduce the pressure and reduce the impact eventually, which might cause failure in near future. So these are basic diagnostics which we can perform if we see a sustained annulus pressure on surface, which could be a simple annulus bleed off and build up test. We can, when we bleed off, we collect the annular fluid, which is call it effluent. We collect it. We can do a composition analysis of that fluid. There could be a leak rate measurements. If the pressure is sustained and if API has defined certain acceptable limits, leak rate limit, if the leak rate is beyond that limit, then it has to be risk assessed. There are two types of communication tests: surface communication and download communication test. I'll come in very soon. So this is an example of a bleed off and build up test, wherein we can record the tubing pressure and the casing pressure. This can be applicable for both the situation during the bleed off and during the build up, after we bleed off, and then when the pressure starts to build up again. What we do is, when we perform a bleed off and build up test, there is an example of tubing and casing annulus only, but we can suppose this is the tubing pressure, this is the A annulus pressure. So subsequently we can do for other annuli also, A, B, C, D, if we have other annuli, and then we plot against time. We have the measurements of pressure against time, and we can see a correlation between, if we see the tubing pressure increase with the casing pressure, or how they could be related to each other. Was somebody trying to ask question?
If somebody have any question, he can unmute himself and ask directly.
I'll pause for a minute. If you have any question, then I can quickly answer. Anybody? I'll wait for a minute.
Hello, Manish. Good morning.
Yeah, good morning, please.
Nice presentation.
Thank you so much, man.
For the sustained annulus pressure, if you are facing a sustained annulus pressure, what's your remedial work to prevent this from happening and from building pressure in the annulus?
Okay, so you're asking what I can do to prevent.
Not prevent, to make a remedial work.
Okay, if I see a sustained annulus pressure which cannot be bled, I'll go one by one, because the remediation for different annuli will be different. For A annuli, it will be different, and B annuli, it will be different. First, we start with the diagnostic. Suppose I have a sustained casing pressure in the A annulus. I will start with diagnostics. I'll do a communication test, try to identify what is leaking into the annulus. Then only I can decide on the remediation. Suppose I see a failure in the tubing by way of communication test, that a certain joint is leaking, or a certain packer or the production packer is leaking. So I have to address accordingly. For leaking tubing, I can utilize a tubing patch. For a leaking packer, sometimes what happens is, because of the moment the packer gets unset, I can try and reset the packer. If that is not happening, or it doesn't work, then what we do is we have an option to put some heavy fluid on top of the packer, which might stop the leak, which might not stop the leak also. Sometimes we perforate the tubing just above packer, put a cement plug, pump cement through the tubing and put displace in the annulus and let it sit down, clear the tubing and restart the well by packer. So there are several options how far or how much you are ready to invest and how much risk can take. A oil well, the remediation for an oil well be different from an injector well. So there are several solutions we have tried here, which have worked, and some have not worked because of not 100% planning, I'll say. If there is some gaps there.
Great. Thank you. Thank you, man.
I'll just add to it, if there is a sustained casing pressure in the B annulus, we do not have a very large portfolio of solutions. We usually top up the annuli with a heavier fluid to subside the surface pressure. There are some fluids which are up to 2 ppg. No, sorry, 2 SG, two specific gravity fluid, which is some cesium format. We displace the small volume into the B annulus, which reduces the surface pressure.
Like pumping resin or some heavier fluids in the annulus.
Yes, I will not recommend for a resin in the cemented annulus, because what happens is we do not know where the leak is coming from. In all probability, it is coming from down below a reservoir. And when we pump resin in the cemented annulus, it might set too shallow and it will mask my problem. So if there is an increase in pressure, I will not be able to see or monitor this pressure. My annulus becomes unmonitorable, and this will create a more risk for me. That's why I will not prefer for resin, yeah, in the cemented annulus. Okay. Somebody was requesting for some break, 1 minute break, or should I continue? If no, then I will continue. Where is my presentation? I think this is the presentation. I'll go forward with the presentation. So this is an example of, I could not share with you the plot, but in the y-axis, it could be a plot for the pressure, and x-axis could be time. And you can plot all the pressures for the A annulus, B annulus, and the tubing. If it is dual completion, you can plot 2 tubing pressure, and then you can see with time how it is changing. Also, you can plot the temperature. If you have a downhole gauge for pressure, temperature, that is an added advantage for diagnostic. Just to see the correlation. This is an example of composition analysis of one of the crude sample. And once you collect hydrocarbon, you can do a composition analysis and compare with your reservoir fluid. Does it match? Is it the same or it is different? Many times we have seen that this composition does not exactly match, but it gives the fraction for the lighter component and the heavier component. It gives you some idea, basically. Otherwise, we have to go for an advanced assessment for this analysis of the collected fluid. This is an example of communication test. So there is surface communication and downhole communication. What I can do is stop sharing this one if I can show something to you. Screen share. So just follow with me here. So a surface communication, what do we do is this is the downhole safety valve. I'm marking. So this is downhole safety valve. What we do is we close this downhole safety valve and bleed the pressure on from top, from the tubing pressure. And we monitor the A annulus. If after bleeding, this pressure also falls off, the A annulus pressure falls off, means there is a communication between any place in the tubing from downhole safety valve to the Christmas tree valve. Okay, this is a simple, very simple communication test. You can also do is, what you can do is, you can, when you close this downhole safety valve, you bleed this pressure, A annulus pressure, and monitor the tubing. So vice versa, you can do and see if the pressure is changing. If there is no change in pressure, then there is no communication here. Other test is called a downhole communication test. In downhole communication test, what we do is we set a plug here. We set a plug here, through tubing plug, and bleed the A annulus pressure and monitor the tubing. We monitor the tubing pressure and see if when we are bleeding this A annulus, is there a change in the tubing pressure or not? If there is a change, that means that there is a hole in anywhere in the tubing. There is a communication from for the tubing failure, this barrier. If there is no change, when we bleed the A annulus and there is no change, that means there is a feed from packer. There is a leak happening from the packer, because it is continuously feeding the A annulus pressure, and when we bleed the A annulus, this pressure is not changing. So these are simple communication tests which we can do to identify what has failed, which barrier has failed within the completion. Any question on this? This is simple communication test, what we usually do. If no question on this one, then I'll move forward for the next diagnostics, which is called the temperature and noise log. So temperature and noise log is a logging tool. It is mostly run in memory mode through stick line. It's called spectral noise log because noise is a frequency. The larger the range of the frequency, the more we can hear, the more distinct frequencies we can hear. Each frequencies have been attributed or assigned by way of research to a certain porous media, the fluid movement within the media, or so they can tell you this frequency, the fluid is moving in the reservoir from rock to rock or carbonate reservoir, or there is the gas is moving from annulus to tubing. So they have some measurements established. Another is the high precision temperature. Together they're called HPT SNL. In normal terminologies, it's called noise and temperature log. So this is a depiction of the log. This primarily is the log, which gives you the depth. These are the depths. And the noise log have been plotted here. The noise is plotted here. So it's like a interpretation fundamentals from a TGT company. Here, what they are saying is, if the flow is through borehole, they have a different frequency. If the flow is through completion elements, it has a different frequency. If it is showing a leak, it has a different. If there is a channeling behind casing, this is the frequency range. So from this analysis, they can tell you where the leak is happening. It's mostly helpful for identifying sustained annulus pressure behind the pipe or behind cement, sometimes within the reservoir. So they also have some analysis for the channels, fractures, large pores, tight formation. So they have different frequencies. How they have come up with, I'm not very sure, but these are now become an industry standard to identify the type of frequency attributed to the flow in certain media. The next example is from one of the wells, I think in this region only, which is showing an injector. If you see on the left hand side, this is an injector being injected, and instead of going into the desired formation, because of failure, it is moving up to the shallower aquifers and being injected here. This is not the intended place of injection. This is not the intended place of injection. When they did the noise log, they found that most of the noise is coming in the shallow region and very less in the region of interest where actual water injection had to be done. So this is an example of the noise and temperature log. Any question on this one? I'm not going into the details of how we run these logs and how do we calibrate with the temperature profiles also. No questions, then I'll move forward. Then these are some examples of advanced log, noise and temperature log I already covered. Then there is a corrosion log or a multi-finger imaging tool logging, which identifies the failure within the tubing. And it can also, if you run both the corrosion and MIT log, you can multi-finger imaging tool, then you can know whether the loss of wall thickness is from inside the tubing or exterior. You can also run cement log, but when we have a tubing, then it is not possible as of now, but there is a technology being developed to run through tubing cement log, which is very promising and coming in future. Cement log could be another. Then there is a production logging tool wherein we can use the temperature and the spinner from this tool to identify the fluid movement or the change in temperature. We can also run downhole cameras, DHS downhole cameras. And the last point is DTS and DAS. DTS stands for digital temperature sensing or digital acoustic sensing, which is similar to noise and temperature log, but using fiber optic cable. So this slide describes the basic principle for DTS or DAS. We have suppose this is the well bore. We run a fiber optic inside the well, fiber optic cable. In some completions, this fiber optic cable is strapped outside the pipe, and if it is not available, then we can run a fiber optic cable within the pipe. Then there are signals which are like electric current, which are sent down the fiber optic cable, and then the backscatter which happens is collected, and the surface interrogator, it is called, surface unit has, and which collects and gives us the interpretation of the temperature profile or the noise profile. The advantage of this is that I'll show you in the next slide, but I would like to read the background for this DTS. DTS data is acquired through a permanent installation of DTS fiber, which I mentioned can be done through the tubing or can be run through a slick line or electric line with the fiber. With completion pumped down the U-shaped control line, this enables continuous monitoring during all phases of well life without the need of intervention. This is when we pre-install it. The fiber optic distributed temperature measurement uses an industrial laser to launch a 10 nanosecond burst of light down the optic fiber. During the passage of each packet of light, a small amount of backscatter from the molecules in the fiber. This backscatter light can be analyzed to measure the temperature profile along the fiber. Because the speed of light is constant, a spectrum of backscatter light can be generated for each meter of the fiber using time sampling, allowing a continuous log of spectra along the fiber to be generated. The advantage of this DTS is shown here. On the y-axis is the depth. Here is the temperature profile, and on the z-axis is the time domain. So once this cable is lowered inside the well, either pre-installed or could be installed later, you can leave it there, and you can change the flow rates within the tubing, within the annulus if you want to bleed, and you can map the temperature with time along the whole depth. So this is a very powerful and very attractive technology for assessing the changes in temperature and pressure along the well bore. In one of the field here in Abu Dhabi, we are using it for gas lift optimization. It helps us to identify flow anomalies and leaks and manage zonal flow without intervention. It gives a 3D output of the analysis, and it is very easy to analyze. You can zoom in. This is very much condensed picture, but the pixel size is so huge, you can zoom in, and you can zoom into maybe 1 or 2 feet also. And the backscatter data is very voluminous. I have dealt with it, and it's pretty good analysis. Okay, so I have added, in addition to what was requested, I have added conductor pipe integrity management, because in offshore, if somebody is dealing in offshore, this is one of the structural member, and the failure of the conductor, if not managed properly, results in total shutdown of the well platform itself. It could result because a failure of this kind can result in falling of one well onto other and damage the whole platform structure also. These are some of the failures which I had taken from internet. So conductor is a well structural component. It shares the load of the inner casings. It has major implications for well integrity, environment sheathing for well casing. It provides an environmental sheathing for the casing, inner casings. And it is the first pipe which should load into the well. The robust design for conductor will ensure that there is no issues later on when we during the life cycle of the well. So if you are not much aware of the offshore wells, if you're not seen it, so this particular thing represents the well conductor. There are guides to support the conductor. There is one guide here. There is one subsurface guide, which is shown here. It is shown here. This is subsurface guide. If the conductor, this is within below the water. The blue represents water, and this represents soil, and this is the ambient. So in offshore, we have 3 regions for the conductor. One is called the ambient or the atmospheric region. Second is the aqueous region, which is in the water, and the third is the portion of the conductor which is beneath the soil, below the seabed. So it's a drive pipe. It is a structural component, a very short length of pipe, the casing which is put into the well, which is the first pipe to go. It prevents, the purpose of this, that it prevents caving, as the shallow section of most of the wells is drilled in unconsolidated soil. It provides support and load for the next casings, protects the surface casing from shallow corrosion, and is considered as the base for the wellhead, and because the starter wellhead starts from the conductor itself. For offshore well, it is exposed to very harsh environment. There are bending and axial loads because of the currents and waves, the natural movement of the wellhead tower also sometimes plays an impact. There are thermal loads because of change in temperature when the well is put on production and shut down. So these add to the additional loads, and of course the vibrations which happens because of the various equipment on the wellhead tower. Very quickly about conductor management, conductor pipe integrity management. We have to ensure a robust design and ensure that is installed at the construction stage. We have to ensure that the loading on the conductor is not too much, or the loading is planned very well by subsequent casings. Once it is installed, we have to ensure protection. The conductor has to be coated, which will prevent it from corrosion, and a cathodic protection system has to be installed, which will protect corrosion for the submerged zone. A routine inspection has to be performed to see or ensure that the degradation by way of corrosion does not happen. And if at all it happens, then we have to undertake some repairs. The picture on the right is showing a rope access technician, it is called. It is hung from the tower, and he performs the thickness measurement at each elevation of the conductor. And on the right hand side, it gives an output of the wall thickness of the conductor pipe, which is measured at the particular elevation. Any questions still now? I have two more sections to go: risk assessment and plug and abandonment. I have only 1 hour left. Any questions from anybody? If no, then I'll move to the next section, which is the risk assessment. These are some reference documents. ISO 16530, which is the ISO standard for well integrated during construction phase and operation phase. The other ISO is 31000 and ICE 31010, which are for risk management and risk assessment respectively. Then there are other guiding documents from IOGP, which is International Association for Oil and Gas Producers, and there's a guide for quantitative risk assessment for offshore, CMPT, and NORSOC standard Z013 also gives us about risk assessment details. So what is the purpose of risk assessment? Because we have to manage risk at all stage of well. So any risk has to be managed, and if there is a risk, it has to be mitigated. The philosophy is that we do a risk assessment, put mitigation plan so that incident does not happen. If an incident has happened, there is no point of doing a risk assessment. So we, at any stage, we look for a potential risk. Based on the available information, we perform a risk assessment for an event which can happen in the future. That's why a probability is considered, because each equipment tend to fail, but when it will fail, that probability has to be assessed accurately. I'll go forward and explain you in detail. So we have to manage all risk related to well. For us, it is well integrity. To assess risk on a well so that it can be managed in a safe and environmentally sound manner with effective use of limited resources. provides an overall understanding of the QRA process and its application for wells. QRA is called qualitative risk assessment. There are other types also, quantitative. I'll just mention in subsequent slides. First, some definitions about hazard, probability, consequence, risk. So a hazard is a potential source of harm. Probability is the likelihood of the hazard occurring. And consequence is if that hazard happens based on the probability, what damage or what is the quantum of damage can happen. And the risk comes as, the definition for risk comes as, it's a combination of both the severity of the consequence of the undesired event and the probability that the event will occur. So in very short form, risk is probability into consequences. So we see the probability, how probable that event is, and how much impact it will make, how much big impact it will make if that event happens, if that failure happens. So in very short words, a risk is a situation involving exposure to danger. This is a picture of, just to explain difference between the probability and the consequences. So this picture is showing us that the consequence, if this person falls inside this hole, is very hard. The damage is, he'll get severely impacted. But here, the consequence is very low. The impact or the damage which will happen to him if he falls in this hole is very less. But the chances of falling here is less. So the probability is low, but the consequence is high. Here, probability is low, consequence is also low. Here, consequence is high, probability is high. So chance of falling this person inside is very high because the distance is large. And here, chance of falling is high, means probability is high, the consequence is low. So this gives us a small snapshot for risk assessment. How do we assess the probability and the consequence? And based on this section will have the lowest risk and this section will have the highest risk. This shows only 3x3 matrix, but in our organization, we are using 6x6 matrix. It's called a risk matrix. So what is the risk assessment process? It will typically involve identification of all types of anomalies and failures related to events that are possible for the wells that are being assessed. Remember, I had mentioned that when we are doing a risk assessment, we are looking for a potential risk or potential failure which might happen in the future. Determination of that potential consequence of each event of the well failure, related events, the consequence can affect the health, the safety, the environment, can cause business interruption. It could be a society impact or a combination of these. Suppose a gas leaks happens and there is a nearby locality where people are staying, then the people have to be evacuated from that area. The production may have to be shut down. If there is any other plant or any other factory nearby, that also may be shut down. So all the impact has to be added together, and that will be the cumulative consequence for that event to happen. And we have to determine the likelihood or the probability of occurrence of that event. Determination of the magnitude of risk for each type of well failure, related event based, or the combined effect of the consequence and likelihood. As I mentioned, that all the consequences which might happen have to be combined together to arrive at the total consequence and the likelihood for that particular event. Likelihood is the probability of the event. So types of risk assessment. First is the qualitative risk assessment, the other is the quantitative risk assessment, and there is another assessment called failure mode and effect and criticality analysis, FMECA. So qualitative is when we do not have the exact probabilities of failure. Like most of the equipment we have in field, we are using like downhole safety valve, Christmas tree valves. We are performing routine testing for them, so we can have a reliability data. Reliable data is, suppose we test 100 valves and we see that there is failure in 5 well. So there is a 5% probability of failure of that particular valve in a year. Suppose we do not have this number for the cement failure. So we apply a qualitative judgment. And then the risk assessment is called a qualitative risk assessment, where we do not have confirmed data. Then it's termed as a qualitative risk. If we have certain and we can quantify the risk, then it is a quantitative risk assessment. And quantitative risk assessment is the preferred method of evaluating, and because it's more reliable and acceptable to the higher management. So risk management will start from risk screening, then we do a risk assessment, and then risk management. So these are the primarily three steps how we do our risk management. So it's a process. Risk screening is the first level of identifying the risk. It's the process to determine if a structured risk assessment should be conducted, or we can just segregate the risk as low or high, and then we perform a detailed risk assessment. And detailed risk assessment will involve the process of detecting the hazard and assessing associated risk. And risk management will allow us to still do the job, but with a lesser risky method. So we might have a small mitigation in place, which will reduce the risk to an acceptable level and allow us to continue operation of the well, whereby the risk is mitigated, the work is performed. However, the level of intervention or the follow-up or monitoring increases. It's called mitigation measures in place, and those actions have to be performed on routine basis so that our threats are continuously monitored and checked. So considerations for determining well integrity risk, we have to follow the basic principle of maintaining 2 barriers. We have to ensure that the shutdown valves are installed and operated and tested. Wells have a potential of higher consequent event due to direct connection to the hydrocarbon reservoir. Because if the barriers fail, then this hydrocarbon will directly release to the atmosphere. We do not have any subsurface barrier connected to the reservoir other than our downhole safety valve, Christmas tree valves, and from outside the well, we have the casings and the cement. Compare it with any surface facilities which are being operated where they are doing a risk assessment, and with the well. For suppose after the well, there are pipelines and pumps and all those things and tanks. Suppose there is a leak in the pipeline, they can just shut down the valve before the leak and after the leak, and the impact is minimized for the portion of the exposed pipe. However, for well, if we lose 2 barriers on top, then we are directly connected to the reservoir, and unless until the well is killed or a relief well drilled, the exposure to the environment is for the whole of the hydrocarbon reservoir. Either the reservoir gets empty or we do an intervention. So the consequences are here when we are dealing with well is way higher than any other asset or any other facility risk. Some of the other considerations for determining risk is the location, whether it is manned, unmanned platform, it's close to habitation, what are the toxicity in the well, whether it is having H2S, whether there is a radioactive. Norm is called naturally occurring radioactive material, or what kind of toxic fluid are there, how high the pressures and temperature are for the well, is well capable to flow naturally, or if the event happens, it'll cease to flow. And ability and the time required to do a relief well, or to do an intervention for killing operations. So these all have to be considered, because till such time the well will continue to flow. Ability to access the well in order to monitor its condition and perform maintenance and repair. So these are the considerations, because when we calculate the consequences, we have to calculate the time for which we'll have this failure, and it will cause a release of hydrocarbon, and the total impact or the total volume of hydrocarbon which will be released to the atmosphere has to be calculated to arrive at the total consequence. So quantitative risk assessment will involve a pre-assessment preparation, wherein we'll select a team, ensure that the required tools are in place. Maybe we require a software, or we require certain diagnostics. Everything all the results have to be in place. Then team assessment review will involve determination of probability and severity of each failure scenarios. Then the well is risk ranked, identify potential mitigation actions and repair actions which can be done, and has to be reported to the management and the concerned stakeholders to perform the task if at all there are some action points. Post-assessment analysis, consider implementation of mitigation and the repair, and use of data management, well-integrated data management. And one point I missed is the lesson learned, which we always ensure that whatever is the lesson learned out of it flows back to the process of evaluation for subsequent operation. So the input required for a risk assessment will involve gathering the wellbore schematic, well barrier diagrams, wellhead pressures, intervention and the diagnostic reports, drilling and completion reports, production data, wellhead facilities, flow line specification, operation, standard operating procedures, etc., etc. So the team, which will comprise of core team, and then there are non-core which can be supported. So these are some of the examples of the members of the risk assessment team who can be involved for the risk assessment. So again, these are the examples of leak paths which I show you continuously after some slides. Why I'm trying to show you this again and again, because when we are doing risk assessment, we have to consider all the scenarios of failures. Depending upon what we see on the surface, we have to see all types of failures which can happen, related failures which can happen for that particular well. And the highest the highest risk is considered that as the risk for the well. So these are some of the scenarios which can cause failure into the well, and the risk for these scenarios are considered, and it is called a scenario-based risk assessment. Some of them could be the possible loss of well control from Christmas tree and down safety valve, possible loss of well control from production annulus, production loss of well control from the cemented annulus, possible loss of well control due to conductor pipe failure, and possible loss of zonal isolation, which will cause subterranean crossflow. This is another example of performing risk assessment, which is called a bow tie analysis. This is wherein we have the threats, and we have the consequences. For the threats, we have to identify the hazards and what are the preventive barriers for these hazards. Similarly, these are the escalation barriers and the major event which will happen if the barriers are not in place. Like if we don't have control plans, emergency response plan, then we may have these kinds of events or incidents. This is just one example of another example of or a technique for assessment. It will again involve data collection, which is, I think, a repetition of the slide, which I mentioned about the well barriers, schematics, handover information, production injection information, performance standards, which are also called operating limits, endless pressure monitoring, diagnostic tests performed, fluid analysis, preventive maintenance activities, corrective maintenance activities, traceability of equipment and replacement parts. Then we come to the risk register. So all the risk have to be tabulated in a particular format at one place. So this will include identifying of hazard, existing safeguards to that hazards, initial risk description, what is the likelihood and the consequence, which will give you the risk level, then planned implementation for the control measures, how we can control that risk. Then based on this implementation, what is the residual risk? This is the example of what I spoke in the previous slide. We identify the hazards. The risk description is here. Then what is the existing safeguards? What is the risk before mitigation? So likelihood and the consequence is the probability and the consequence, which the product of which is gives us the risk. And then once the mitigation control measures are there, and what is the residual risk after mitigation? This is just an example. And these are the headers. These are the top headers. These are the headers, and a detail mention is mentioned here in the description. This is from ISO 16530. These are the header information and the description, what needs to be captured here in for each of the headers for creating the risk register. This is higher the probability, higher the consequence, greater is the risk. This just came. So this is 1, 2, 3, 4, 5, 1, 2, 5 by 5 matrix. This is 5 by 5 matrix. This is part of the qualitative risk assessment. This is one of the example of event tree for determining the probability. So it is giving us how we calculate the probability of failure for a particular scenario. So we have probability of failure of each of the components, like hole develops in flow line, washout, choke. This is 0.5% per year. Drop in flow line pressure for ESD. What will happen is there will be a drop in pressure when this failure happens. What are the control measures? SSV, surface shutdown valve fails to close. This is the probability that it will fail to close. And this is the probability that it will close. So this is an expected event and this is not an expected event. So next is DHSV fails to close is 3.93%. And DHSV closes is, this is surface shutdown valve and this is downhole safety valve. So we have all the probability. So if we choose the failure of the failure path is this. So this will result in release of continuous until manual valves are closed of failure. So then we do a cumulative probability to arrive at the probability of failure for this event to happen. Because this fails, this fails, this fails, this fails, and then the actual event is happening, a failure event is happening. So this is the probability of event which is happening, and the risk matrix we see this probability is under which category. So that will be the probability of failure and the consequence out of this. So probability and consequence will give the risk level for us. So consequence severity determination, how do we do, or how do we calculate the consequence or the severity of an event? So we look for the impact on the people, the consequences. So suppose a person gets injured, it will have a certain consequence. A person is away from work, suppose 5 people get injured, 1 people get killed, 5 people get killed. So these have different level of consequences. The impact on the environment, similarly, how much is the release to the atmosphere? Similarly, there is we calculate for company reputation and the direct financial impact and the production loss. So all these can be calculated, and the consequence level for that failure to occur can be established. Here we calculate the probability, and in this slide we are calculating the consequence. Multiple or a combination of probability of failure and the consequence will give the threat level or risk level. So these are some of the data sources which are used to establish the probabilities. So these are published data available. Allard principle I tried to explain yesterday. Today again, this is the risk level, this is cost, and this is cost per gain. So as the cost per gain increases, the risk level drops. However, the resources and effort goes higher and higher as we increase the cost. So we have to arrive at a point where this point is called ALARP level, which is as low as reasonable practicable. Some of the other terms which will be available in the internet are SFAIRP or LARP. I do not remember the full form of these, but these are widely used industry standards which are available. So these are some examples of the hazards which we use for our risk assessment. Starting with the first one, which if I say that if there is a possibility of loss of control from Christmas tree and down safety valve, what could trigger this event? In what scenario this event can happen or this hazard can happen is possible by hit by a vessel. If the well is hit by a vessel, barge movement or rig movement, or by a truck on surface facilities, or surface Christmas tree, and others are offshore for offshore, or there could be a leak from Christmas tree body, there could be a leak from cavity. So each scenarios are evaluated in the risk assessment. Each is that. So what is the probability of this event happening, Each will have a different probability of event happening. And for that particular well, based on the production or the type of fluid, the consequence has to be determined. Similarly, the second hazard is possible loss of well control from annuli. Possible loss of well control due to conductor pipe failure. And what could cause these? We have the probability of failure of this event, which will cause this event. And once this happens, what is the consequence or impact? Consequence or impact to people, asset, etc., etc. I forgot. Yeah, the consequence on people, environment, company reputation. So we have to establish the consequence based on that particular scenario. And there could be several scenarios, such scenarios, which needs to be evaluated for a particular well. So I have listed only a few of the scenarios, but there are several other scenarios which need to be considered. Whatever you can think for, based on your location of the well, the impact on the environment, whatever could be. I tried to be quick on this. Any questions till now? I know it is very boring risk assessment, and it is mostly theoretical and task driven. If you, unless until you do it, you will not appreciate the effort. Okay, then I'll try and move forward. Again, we come back to the life cycle phases. Now we are on the last phase, which is the abandonment phase, where we have to restore the barriers which we had intervened while accessing the reservoir, or the target zone, phase zone. So what are the objective? We have to establish the permanent barriers, as the well will have no future use. So preventing formation and wellbore fluid from escaping into the environment. Prevent cross flow between the different reservoirs or discrete zones which were penetrated. And also we have to ensure that the shallow aquifers are not contaminated with the reservoir fluids or with hydrocarbons. So this is the well which is operating. Suppose these are the two pay zones. We have to establish primary and secondary barrier independently for these pay zones. Each penetrated pay zones have to have their own primary and secondary barrier. In addition to, there is a requirement to have a surface plug, which is also called an environment plug. The last task is to, once these all barriers are in place, tested, everything done, then the last task is to cut the casing from the seabed for offshore, and onshore it is from the surface, and cover up the surface with mud, sand, whatever is the area. This picture is again repetition from yesterday. This is the reservoir, our reservoir pay zone. Black was the cap rock which we had penetrated to access the reservoir. When we drilled, we had a primary barrier and a secondary barrier for the well when it was in operation. Now we have to restore this barrier. We have to restore this plug and have an additional plug on top of it, which will be as a secondary barrier during P&A stage. So what will require to be done at the P&A stage? First, we have to assess the integrity of the well. Whether we are having any pressure in the cemented annulus, the concern, those have to be repaired before we complete the P&A. And we should not leave any leaking path behind the casings. So mitigation is required for all sorts of hazards. Well barrier plans and schematic needs to be created. Barrier verification methods prior to and during abandonment has to be documented and implemented at the execution stage. Requirements from well design phase may be pertinent to the well abandonment phase and should be incorporated into the abandonment program. So many times when we design a well, we consider certain aspects which will be required during the abandonment stage, like not bringing cement to the surface for inner casing could be one of the requirement, or not having cable to the top of packer could be another requirement if we are doing a rigless P&A. Without complicating the situation, so some of the P&A consideration can be done at the well-designed stage also. This is just the message I would like to convey. The P&A operation, when we are performing the P&A operation, could be divided into 3 or 4 distinct phases. The first will be the preparatory work, when we do the planning process. We can start with killing the well, removing the tubing, etc., clearing the well, then doing the reservoir abandonment, then intermediate abandonment, and the final is the wellhead and conductor removal. So the benefit of dividing the full operation sequence into distinct phases is to highlight the opportunity for performing simpler parts of the P&A operations by rigless method instead of more traditional and costly rig-based method. So when we have distinct stages, we can see that some of the stage can be, or the phase, we do it by riglessly or by barge or by coil tubing or something like this, so that we will save some costs for the rig, because final P&A operation has to be performed by rig. As much as we can reduce the rig time, we will be able to save our costs. The next task is to identify the hazards. The initial well design, well construction, and any intervention activity should be taken into consideration for the end of well life abandonment requirement. The hazards which should be considered are the identification of all potential source of flow that can be exist at the time of abandonment, including any failures of cement or casings which have happened or which are known during the well production or well operation stage. Potential flow, future flow sources due to reservoir repressurizations also needs to be considered. Depletion of a reservoir leading to potential for cross flow to other permeable zone, and identification of all potential leak paths have to be considered in this stage of identifying hazard, so that we are able to create a more robust P&A plan. So barrier considerations for abandonment. Abandonment considerations in design and construction phase have to be the location. These are the location of the plugs where we have to place. So the plugs are supposed to be placed at competent formation or the cap rocks. Assurance that the surface casing is cemented to the surface and all shallow aquifers are properly isolated to avoid any contamination of the aquifer with the reservoir fluid. Options to establish permanent barriers to all potential leak paths at abandonment stage. Capacity to verify annular cement isolation effectiveness. So many times we have to put cement behind the pipe, behind the casing, I'll say, where there had been poor cementation at the earlier stage. But the challenge still remains how we verify the cement behind the pipe. There should be capacity to access well sections for placement of internal cement, internal permanent cement plugs. Then completion is to avoid control lines at the intended well barrier depth. So when we are setting a cement plug with completion in place, this picture shows that the completion has been removed, but in certain cases we may allow the completions to be inside the well while we are putting the cement plugs. So while the completion or the tubing string is inside the hole, inside the casing, we have to ensure that we do not have any control lines, because that becomes the leaking point or the leak path for the hydrocarbon to migrate to the surface. There should be 2 independently tested barriers towards the reservoir, which is a mandatory requirement. Where 2 independent barriers are specified, the integrity of the second barrier shall not be reliant on the integrity of the first barrier, which means that they should be independently tested. The only permanent barrier shall be verified by open hole cement plugs, verified cement plugs inside the cement casing. By verified cement plug means that it has to be pressure tested. Mechanical plugs and bridge packers are not considered as a permanent barrier for permanent abandonment because they have a potential to degrade. The elastomers are have potential to degrade and eventually leak in future. So a bridge plug or a packer cannot be considered as a permanent barrier. However, they can be used as a base to put cement plug on the top. The cement behind the casing shall be verified to be of good quality to qualify as a well barrier. How can we verify it? We can verify by pressure test or cement log. If the sufficient length of good cement cannot be confirmed from the cement job records and old logs, a cement evaluation log shall be run, which I just mentioned. If the cement cannot be established to be of good quality, remediation cement shall be carried out. Any fluid bearing formation in the overburden section, such as high pressure zones and hydrocarbon containing formation, should be isolated with 2 independent barriers. An open hole to surface plug, environmental plug, shall be installed below the seabed, which prevents any residual fluid contamination to the environment. So this is not a pressure tested plug, but a plug just to prevent if there is any residual hydrocarbon remaining, which should not flow to the environment and pollute it. How do we place the barrier? The barrier has to extend horizontally and vertically. Both are being specified. The length of the barrier is usually 50 meter or 150 feet, and the extent has to be within a competent formation, or as we call it, rock to rock isolation, which means that the formation here has to be competent. Could be a cap rock, a cap rock, or a low permeable rock. So permanent well barrier shall extend across the full cross section of the well, including all NLI. So if there are subsequent pipes, all the plugs have to be in place, including all NLI and seals, both vertically and horizontally, as mentioned in the picture. The well barrier shall be placed adjacent to a low permeable or a impermeable formation. So this formation has to be competent, low permeability or impermeable, or also cap rock if is available, with sufficient formation integrity for maximum anticipated pressure. This I'll come to the next slide. So what is meant by maximum anticipated pressure? I'll try and explain the plot on the right hand slide. The dark one is the pore pressure. I'll not cover all, just see the fracture pressure and the gas column pressure. So this is the gas column pressure, and the fracture pressure is this line which is following it. So at this point, the gas pressure is exceeding the formation pressure at this point. So my plug has to be to act as a barrier, to act as a barrier for this gas column, my plug has to be below the point where the gas pressure is exceeding the formation strength. I'll repeat one more time. The plug has to be as close as low as possible at a location where the formation strength is higher, where this strength is higher, this pressure is higher than the gas pressure. If I place this plug where the strength is lower, this gas pressure will break the formation here. So my plug cannot be shallow to have a barrier for this particular gas column. I hope it is clear. So well barrier shall be positioned at a depth where the estimated formation frac pressure at the base of the plug is in excess to the potential leak pressure. So the frac pressure of the rock should be higher than the potential internal pressure. Barrier placement is determined by comparison of the frac gradient in the cap rock above the hydrocarbon zone with the gas gradient above the same hydrocarbon zone. Barrier should be placed deep enough so that the fracture gradient at the same depth is greater than the gas gradient for the hydrocarbon. So it is the same thing mentioned in 3 different types. So this determines or this helps us to give us the placement of the plug, the location of the plug. We have the length of the plug, location of the plug, the material of the plug is specified. What is the verification method of the plug is defined. So all these become the part of the P&A program.
Sorry, Manish, what is the wellhead pressure of the gas? The surface pressure.
So surface pressure will be here.
Yes.
Yes, please. So this is the gas gradient, no? Gas column C. This yellow thing is the gas column. The surface pressure as per this chart is between 150 bar. Any confusion here?
Yeah, 150 bar. According
Yes,
to
please.
what?
Yes, please. As per this chart.
According to the mass or what value?
Ah, okay. So mass. So remember we are in the P&A stage. We have removed all the internal tubings. We are now placing the plugs. We are deciding on the position of the plugs, which is the cement plugs as primary barrier and the secondary barrier. Here I am trying to explain that we have to place a plug which will form a rock to rock isolation. Suppose this is the wellbore and the rock is outside. So we have to place a plug where there is a competent formation, which I explained in the previous slide. And here I'm telling the location of the plug, which has to be at a place where the rock strength is higher than the gas pressure or the pressure of the hydrocarbon zone. Here we are not looking at the mass of the well because we are in the P&A stage. Is it okay, or should I expand?
Yeah, but I don't know the source of 150 psi.
No. This is the hypothetical case. This is not any. As I mentioned, I've just taken some plots from the internet.
Okay.
Yeah. This is just for explanation purpose. No, this is not any may not be any well attributed. Maybe some paper.
Excellent, much. Thank you.
Most welcome. So well barrier verification. So well barrier verification, once the well barrier has been constructed, its integrity shall be validated by leak testing, which is pressure testing, weight testing, cement plugs that cannot be pressure tested. A zero leak rate shall be observed and recorded for at least 10 minutes after stabilization. So leak testing could be a positive pressure test, and if possible, in certain cases, if the opportunity comes, is there, then we can do a negative test also for the barrier. The final stage is the removing the equipment from the seabed or the Christmas tree from the land area. For P&A wells, the wellhead and casing shall be removed below the seabed at a depth which ensures no stick up in the future. They could be 1 feet or 2 feet, depending upon the vessel movement requirement. The required cutting depth shall be sufficient to prevent conflict with other marine activities. The location should be inspected to ensure no obstructions related to drilling and well activities are not left behind on the seafloor. This is on the right side. There's a picture of diamond wire saw, which is used to cut the conductor from the seabed. So last point is monitoring of P&A wells. In order to have a proper and effective monitoring after completing the P&A, a program for visual inspection shall be established. The frequency shall be established by a risk assessment and should not exceed 5 years for all P&A wells. All P&A well status to be confirmed by seabed survey. If there is a leak, further action to be considered to stop the leak immediately. Somebody had asked question, if fully P&A well leaks, what are the options and how we can reinstate the barriers. Yeah. I think we are close to the end. These are some of the standards or some of the documents which can help you to prepare a P&A program or guidance for doing a P&A. The first document is from a DNV. It's a risk-based abandonment of the well. This is very much in vogue these days because of cost implications for doing the P&A, and putting the minimum barriers or fit for purpose barriers is the need of the hour to optimize on the P&A cost. Then there is API RP 65-3, which is a very recent document which was being issued by API, which is deals with the wellbore plugging and abandonment. And then there is overview of international offshore decommissioning regulations, volume 2, wells plugging and abandonment. It's an IOGP document, International Association for Oil and Gas Producer. And also D10, of course, gives us all the barrier requirements and the testing requirements. How do we do the verification? That's all for today. Thank you so much. We managed to complete within the time frame which was given to me. I try to be fast. If I skip something very fast, please do let me know. I'll try and take it one more time or repeat it. These are very lengthy topics, believe me. If I do each topic one day, it might be justified. But I try to squeeze in as much as information within a short period of time. I try and do that way. Questions, comments, I can share my email if you want to communicate with me, ask questions, clarifications. You are most welcome.
Thank you, Mr. Manish. Thanks for this informative 2 webinars. And from the feedback that I got from the attendance registration, it's all positive feedback of the sessions. So thank you for delivering this valuable content for us. And if anyone has any question, please, you can unmute yourself and ask it directly.
Thanks for your patience, everybody. And I'll appreciate again one more time if you have any questions, any clarifications, I can be of any help. I would like to be associated with you guys to help you in future if at all the need arises. But I'll encourage everybody to be a member of SP technical sections as much as possible to gain knowledge. If you read through those sections, you will definitely gain lots of information. You can ask the industry experts of any problems, your challenges, your career guidance. The people are there to help. Believe me, you can raise any kind of professional or your career related personal requirement, people are there. Just seek out, be involved with the community, SP community, and try and gain as much as possible from their experience, industry experience. And they may probably guide you for your career also.
Hello, Manish. I have 2 points.
Yes, please.
Yes, first one, you mentioned a good list about leak detection in the annulus, how to determine the communication point in the tubing, in the casing, what is the barrier which is leaking. Very good list. What you can add some electromagnetic logs and ultrasonic ones like the new Schlumberger epilogue that is used for multiple casing evaluation.
Yes, yes, yes. Multi-barrier corrosion log.
Yep, excellent.
Definitely, definitely. Thank you so much.
And for the second point, what is the difference between mass calculation and gas lifted wells on the natural fluids?
So the basic ground rule remains the same. If I can understand your question is about the mass calculation for natural flow wells and a gas
Right.
lifted well.
Yeah.
Right. So ultimately, you have to define the operating limit or the limits for your each barrier element. So the basic philosophy or calculation for a normal well and a gas lifted well remains the same for the production annulus. As you move to the cemented annulus, the first cemented annulus, you have to be careful from the well construction point of view. I'm more concerned about designing and delivering a well which is compatible for a gas lifted well rather than having less considerations or no consideration for a gas lifted well when the well is put on gas lift. From calculation perspective, there will not be any difference for calculation. The methodology of calculation will remain the same. However, you have to see the scenario of the event of gas leaking from the A annulus to the B annulus. You have to construct the well to meet or to be safe if this scenario happens. And the barriers you need to consider. Suppose your cement behind the 1338 surface casing is not enough, then it lead to problem. Your casing has to be gas tight, the second casing, because in the event of the gas leaking from production annulus to the subsequent annulus will create a problem because if your casing is not gas tight. So your emphasis should be on delivering or at the time of the well construction stage. This is what I am trying to express.
Yeah, right.
But the methodology for the calculation will remain the same for the mass calculation.
Excellent, Manish.
Most welcome.
We talked at the beginning about the annulus remedial work by pumping a resin or a chemical in the annulus to tubing fluid the cement. I remember that some service companies like Sibru has annulus intervention equipment that can go down from the wellhead to tag the cement in the annulus and pump the chemical directly above the cement, not by lubricate and bleed method.
Correct. So there is a company called Expro. They have taken over this. Before it was supposed to be called Cars. Now it is called Aquapoda.
Yeah.
Octopoda, sorry, not Aquapoda. Octopoda. Now the challenge with this is that you are intervening in an annulus which is a cemented annulus behind the 1338 casing, in which my company regulation says that behind 1338 cement should be to the surface.
Good.
Okay,
Yeah, very good
so
point.
I do not have any option to lower this coil tubing into the into this annulus, which is behind the 1338, between the 1338 and the outside. Sorry, the production casing and the surface casing. Sorry, in the B annulus. So B annulus, my cement should be onto the surface, but which is so many times I may not be able to lower. So if I am able to lower this coil, the thin coil, only 1,000 feet or 500 feet, even then there I cannot place a barrier there. I have to rely on lubricate and bleed with a heavier fluid. because I do not want to mask a problem. Suppose the leakage is from bottom, and the small area which will be left for fluid expansion might create a problem for me. My main challenge is masking the problem. I should be able to monitor my surface pressure, whatever intervention I do in such scenario.
Good point. Thank you much.
Yes.
I think we don't have any more questions. Once again, thank you.
Thank you so much.
And everyone have a good time.
You too also have a good day, very good day, and a nice Sunday. Thank you for your team for organizing this webinar, and appreciate your passion to learn more and more by arranging different seminars and webinars. And I really appreciate your passion to learn more and more. I wish you all the best, and anything I can help, do reach out to me.
I'm glad to
wish you
hear
all the
that, and we met you in person. Thanks.
You're most welcome whenever you come to Abu Dhabi. Do just text me. I'll be definitely willing to meet you.
Of course, inshallah. Thanks again.
Have